Have you ever looked at the world around you, everything from a grain of salt to a steel beam, and wondered if there's a hidden order to it all? A secret set of rules? Well, there is, and today we're going to unpack that beautiful, invisible structure. Our journey kicks off with a really simple but powerful idea.
It all starts right here. Imagine this: an infinitely repeating grid, kind of like a cosmic scaffolding that fills all of space. This is the foundation, that quiet rhythm that underpins the structure of pretty much every solid material that you can think of.
So, okay, we've got this invisible grid. How do you actually build a real crystal from that? Well, it turns out there's a simple three-step creed, a core belief system that every single crystal follows. So, first you start with the grid itself, which we call the lattice. It's really just an abstract set of points. Step 2, you decide what to put on those points. An atom, a molecule, let's call it a bead. This is what we call the motif. And third, and this is the key, you find the smallest repeating box that contains that pattern. That little box is the room, or what scientists call the unit cell.
And really, the true power is all packed into that one unit cell. Think about it. This single, tiny room holds all the DNA of the crystal. If you know its dimensions, its size, and the angles of its corners, you can perfectly reconstruct the entire thing, no matter how big it gets. It is the ultimate blueprint.
But here's the catch. Nature has rules. You can't just make these unit cell rooms any old shape you want. There are strict architectural laws, and they're all governed by symmetry. And these laws dictate the fundamental shapes a crystal is allowed to have.
And based on those rules of symmetry, it turns out there are only just seven fundamental shapes these unit cells can take. These are the 7 crystal systems you see here. They range from the completely lopsided, squashed box of the triclinic system all the way up to the perfect, beautiful symmetry of the cubic system. And what's amazing is that every single crystal in the universe has to fit into one of these 7 categories. So what is symmetry, anyway? You can think of it as a kind of turning game. It's any move you can make, a spin, a flip, a reflection, that leaves the crystal looking completely identical to how it started. It's nature's little trick for creating patterns that are both super complex and incredibly orderly at the same time.
Now, these moves come in a few different flavors. You've got your basic ones, like spinning the crystal around an axis or reflecting it like it's looking in a mirror. But then you get these really beautiful, more complex moves. Things like a glide, which is a slide and then a reflect, or a screw, which is a twist and then a step forward. It's almost like a tiny choreographed dance for atoms. And this illustrates one of nature's most fascinating and weirdly strict rules. You can have 2-fold, 3-fold, 4-fold, or 6-fold rotational symmetry, but you can never have 5-fold. Why? Well, because you simply can't tile a flat surface with regular pentagons without leaving gaps. Go ahead, try it. It's impossible. And since crystals have to fill all of space, 5-fold symmetry is basically forbidden. Okay, so we have the rules of the game, we have the shapes of the rooms. Now let's see how the players, the atoms themselves, actually like to arrange themselves inside those rooms.
You know, atoms are pretty efficient. They like to settle into arrangements that are stable and tightly packed. And because of that, you see these 3 structures pop up all the time. There's body-centered cubic, or BCC, where you have an atom at the corners and one right in the middle. Then there's face-centered cubic, FCC, with an atom on each face. And finally, hexagonal close-packed, or HCP. In fact, FCC and HCP are nature's absolute tightest, most efficient ways to pack a bunch of spheres together.
Now, it would be so easy to think of crystals as these perfect, flawless, pristine little things. But the truth, and honestly the thing that makes them so incredibly useful, is that they are almost never perfect. This line just gets right to the heart of it. The imperfections, those tiny little mistakes in the pattern, they aren't just flaws. They are often the most important part of what makes a crystal what it is, giving it the properties we depend on every single day. It's actually these defects, a missing atom here, an extra one squeezed in there, or an entire mismatched row called a dislocation, that give materials their most amazing properties. It is literally what allows a piece of metal to bend instead of just shattering. Without these imperfections, solid materials would be incredibly brittle and a whole lot less useful to us.
Okay, this all sounds great, right? But it brings up a huge question. If all of this stuff is happening on the atomic scale, millions of times smaller than we can see, how on earth do we know any of it is actually real?
The answer is just brilliantly simple in its concept. We take a beam of high-energy X-rays and we shine it right at the crystal. The crystal's orderly planes of atoms inside act like a really complex set of mirrors, and they scatter those X-rays in a very specific, very predictable pattern.
And that pattern is governed by this incredibly elegant little equation, Bragg's law. By measuring the angles where the X-rays come bouncing out, we can use this law to calculate d, which is the exact distance between the layers of atoms. The pattern we see is a unique fingerprint that tells us literally everything about the crystal's hidden internal structure.
So, we've gone from grids to unit cells, from symmetry to defects. But what's the payoff? Why does understanding this deep, hidden order actually matter so much?
Well, it all comes down to one thing. Structure determines everything. The way those atoms are arranged is what dictates how a metal bends. It's why a diamond shines, it's how a battery stores energy, and it's why a material might be strong in one direction but weak in another. By understanding the structure, we can predict and even start to design the properties of any material we want.
And it all comes right back to this one powerful idea. The entire macroscopic world of materials, with all of their incredible, amazing properties, can be traced all the way back to the shape and the contents of one simple repeating room.
And that, right there, is the essence of crystallography. It's the science of seeing the invisible, of understanding the fundamental patterns that build our world, and then using that knowledge to engineer the future.
So the next time you look at anything solid, remember the incredible, ordered world that's hiding just beneath the surface. It really makes you wonder, doesn't it? What other invisible patterns are out there just waiting to be discovered?